In this video, we're going to look at radioactive decay and how we can predict how elements can transform if we change their nucleus. So this will be a good introduction to nuclear and atomic physics. To start off, let's talk about some notation that we're going to use throughout this unit to help us understand what's going on inside the nucleus. This is what we're going to call our standard notation. You'll notice here, sometimes we'll call it AZX notation. So you'll see this is kind of the placeholder for what that might look like. But here's an example of what this looks like in practice. The symbol here is the element that we're having. So this is aluminum. You can see that in the periodic table square itself. Now you'll also notice some other numbers that are here. This top, or the bottom number rather, is the atomic number. Aluminum is number 13 on the periodic table, which means that it has 13 protons. So we're going to write that atomic number on the bottom left. The top left number here, 27, you'll notice is really close to the average atomic mass. This is the atomic mass or the mass number for that particular atom of aluminum. Both of these will always be a whole number, and they can help you understand how many protons and how many neutrons are inside the nucleus for that particular atom of that element. If we look at this, from this notation, you should be able to identify four main properties. You should know the mass number, and you should be able to know the atomic number. The atomic number you can see is 11. That is showing up for sodium, how it is on the periodic table. That atomic number of 11 means that there are 11 protons in an atom of sodium. Now, the mass number is 23. Mass number is a way of telling us how many protons and neutrons are inside the nucleus. For now, let's just assume that they each have a mass of 1. So one proton is a mass of 1. One neutron is a mass of 1. So if the mass overall is 23, that means I need to have 23 combined protons and neutrons. Those are things that are inside the nucleus, so we call them nucleons, most likely. We are going to need 23, so the number of neutrons must be 12. So 11 protons, 12 neutrons gives us a mass of 23. Over here for magnesium, we see that it has 12 protons and 13 neutrons. Well, 12 protons is going to give us the atomic number. It's always defined by the number of protons. The mass number, again, is the same as the number of protons plus the number of neutrons. If I have 12 and 13, that means I have a mass number of 25. So the way we'll write this magnesium atom in standard notation is Mg with a 25 and a 12. With this, sometimes IB will ask you a question like this. A nucleus of californium, which is a real element, contains 98 protons and 154 neutrons. Which of the following correctly identifies the nucleus of californium? You just need to know how these numbers are situated. Remember that bottom number is the atomic number. The atomic number is always the number of protons. So I know for sure it can't be this top left and it can't be the bottom right. It needs to be a number with 98 on the bottom. And then the top number is not the number of neutrons. Instead, it is the number of neutrons plus protons, the mass number. So our correct answer here is 252, which is 98 plus 154. All right, some more notation and vocabulary that you need to know. There are two words that we'll use frequently throughout this unit, isotope and nuclide. Well, isotopes, you might remember from your chemistry days, is looking at different versions of an element and the atoms that that element can take on. So here a great example is carbon. Carbon can be found in a couple different masses, carbon 12 or carbon 14, and some others as well. These are both isotopes of carbon. Sometimes they'll call them flavors of carbon. They're both carbon, which means they both have the same number of protons because 6 protons is always an element, carbon. And in this case, they have different numbers of protons. That's what makes the mass number different, but the atomic number the same. So we call these isotopes of each other. That they are isotopes of carbon. Another word that we'll use throughout is a word called nuclide. Nuclide is just a way of talking about one particular atom's configuration. So this is a single configuration of an atom. So if I were giving you an example here of carbon 14, I would say a nuclide, this nuclide of carbon. Um, Very specifically, the configuration in this case, where it has 6 protons and 8 neutrons to give me a mass number of 14. Another thing that you're going to need to know to understand what's going on inside of radioactive decay is fundamental forces. Forces play a huge role in our understanding of the atom. Here, you'll remember Coulomb's law. Coulomb's law tells us the force of attraction or repulsion between two charged objects. Well, you probably know that inside the nucleus we have protons and neutrons. Protons are positively charged, neutrons are neutral. On the outside, we have these electrons that are kind of orbiting around or finding themselves in this probabilistic orbital cloud around that nucleus. Well, you might remember that opposite charges attract and like charges repel. These electrons, being negatively charged, are attracted to the positively charged nucleus, which keeps them kind of around that nucleus. Well, if I use that same logic, I can see where that, if that force alone is the only one, that breaks down pretty quickly because inside the nucleus, I have a really, really compact collection of protons and neutrons. All the protons are positively charged. So Coulomb's law tells us that positively charged protons shouldn't be able to be next to other positively charged protons. Those like charges should repel. So there are some other forces that are factoring in here. These are the four fundamental forces: strong nuclear force, electromagnetic force, like Coulomb's law, gravitational force, like we've talked about in the past between two massive objects, and the weak nuclear force. Right now, I want to focus on this strong nuclear force because this is the force that allows those protons to be able to be clumped together so tightly inside that nucleus. This strong nuclear force, it takes place over a very, very short range, and as the name implies, it is very strong. Um, Many orders of magnitude stronger than electromagnetic force or gravitational force. Now, a good conceptual understanding of how something can be very short range and very strong is to think of these protons uh, covered up in like a Velcro substance. This is not, for the record, how the strong nuclear force works, but the range is so short that these protons need to basically be touching. Just like Velcro can apply this force that holds things that don't want to be next to each other, it can hold them together. But if they're just a little bit separated, that force does essentially nothing. It's not enough to keep the two things together because that Velcro isn't touching. So this Velcro of the strong nuclear force can keep these protons together even though they don't want to be next to each other. Well, they don't want anything. The two positively charged protons have this force of repulsion because of Coulomb's law, but the strong nuclear force overcomes that and keeps them together. So, it's kind of this balancing act then. If you get a lot of protons inside a nucleus, the force of repulsion from that Coulomb's law, Coulomb's force, to try to push those protons out becomes really, really large because there's a lot of positive charges trying to repel those other positive charges. So, because of that, when we get larger and larger nuclei, you're going to notice that there's a bunch of neutrons that are added in there. These neutrons kind of serve as a buffer between these repelling protons. They experience the strong nuclear force, but they don't have a charge, so that there is not this Coulomb's force or Coulomb's law sending this repulsion between all the subatomic particles. Those neutrons are separate from that, and they can just serve to stick everything together. And what you'll notice there is if you were to graph the different elements that form in their stable way, at the very beginning of the periodic table, the smaller elements, you might have noticed in your chemistry days that the number of protons often equaled the number of neutrons. For example, carbon is typically carbon 12. That means there's 6 protons and 6 neutrons. They are the same. But as you get larger and larger, you'll notice that that balance doesn't hold true, that the number of neutrons is the same as the number of protons. Instead, the larger the atom is, the more it's skewed towards the number of neutrons. Now, this line that forms, kind of this area has a name. We call that the line or the valley of stability. That these are the combination of protons and neutrons that are able to form this stable nucleus, that it isn't too much repulsion force to send those protons out. Well, not every atom that forms is automatically on this line of stability. If it is not, it undergoes a couple different processes to become stable. And that is what's going to get us to this idea of radioactivity and radiation. So, radioactivity is this process where these unstable nuclei, these unstable elements, decay into new elements, and in the process, they release particles and or waves. Basically, just lots of energy, sometimes spitting out protons and neutrons, sometimes transforming a proton into a neutron or vice versa, and sometimes just emitting energy in the form of gamma radiation. So we're going to look at all these different forms of decay, what they mean, and how we can use them to predict what's going to happen to these atoms. So the first is called alpha decay. This is when an unstable nucleus sheds an alpha particle. An alpha particle is just a little cluster of two protons and two neutrons together. In doing so, it becomes more stable because the nuclei or the nucleus becomes a little bit smaller. Now, two protons and two neutrons is actually exactly the same thing as a helium nucleus. Helium has two protons and a mass of 4. So the way that we're going to write this, we're going to write this in a nuclear reaction notation that we're going to start with what we call the parent nuclide. Remember, nuclide just means the configuration of that atom. So the parent nuclide, and then we're going to end up with a daughter nuclide. That daughter nuclide is going to be just like the parent, only it's going to have two less protons. So that Z number, that bottom number, goes down by 2, and it's going to have a mass that is 4 less because it lost 2 protons as well as 2 neutrons. Each of them have a mass of 1, so it's a mass of 4 overall. And you'll notice that we get this alpha particle, this helium nucleus, out of the deal as well. Well, an easy way to do this is to look at the numbers. If I start with uranium, uranium is 238.92. My mass number has to go down by 4. So that 238 goes down to be 234. My proton number, my atomic number goes down by 2, so 92 becomes 90. So uranium 238 turns into thorium, which has an atomic number of 90 and a mass of 234. So that is alpha decay. We can see some different ways that you might have to predict this. If you see that radium 222 decays into radon 218, you can look at the numbers here and see that it lost a mass of 4 and it lost an atomic number of 2. 4,2 we know is the same thing as a helium nucleus, so we can write that as a 4,2 helium. You'll notice down below, there's another way that we could have written this. Sometimes we'll describe the alpha particle with just the Greek symbol or the Greek letter alpha. Both of these are appropriate in the way that you might write these nuclear reactions. So here I've got that 4,2. I started with 208, which means that's going to go down to 204, and 84 turns into 82, and that is an element of lead. If you weren't given what that element is, you could still figure it out as long as you have a periodic table and can look up what 82 is. So find 82 on the periodic table, you'll find that that is lead. Lead has an atomic number of 82. Our next type of decay is called beta decay. There are two types of beta decay. So let's start with beta negative decay. This one's kind of weird, so buckle up. We have an unstable nucleus. Sometimes the neutral neutron is converted into a positive proton and a negative electron. So we start with a neutron. That neutron has a charge of 0. Now, that charge has to remain 0. You can't have a charge that changes because of something called the conservation of charge. So if that neutron is going to turn into a proton, which can happen, doesn't happen all the time, but it can happen to become more stable inside that nucleus, it can't just become a proton and nothing else because a proton is a positive charge and the neutron had no charge. So in the process, it also produces an electron. So this proton and electron together still have a charge of 0. The proton is a positive 1. The electron is a charge of negative 1. They have this charge of 0. You'll notice it also produces this other little particle. That's a special particle that we'll talk about in more detail later on. It's a lepton known as an antineutrino. So you'll see in this right up here, this reaction, we have a neutron, which we'll write like this. We'll talk about that in a minute. Gives way to a proton, an electron, and this antineutrino. Notice that little bar on top. We're going to see that again. That represents anti. So we'll see a variety of different particles that have antiparticles as well. And the way that we differentiate between the two is this bar on the top. So beta negative decay can be described in a couple different ways. One of my favorite things is there's a website called the Particle Zoo that sells all sorts of these little plush, adorable particles. And one of the things that they sell for a mere $50 is a beta decay set, and they have the little particles inside them. The neutron pouch opens up and it flips into a proton. It's really cool. Totally worth $50. Well, this beta negative decay, if we are looking at the atom as a whole, not just the neutron turning into a proton, we can see what it does to the atom itself. This parent nuclide undergoes this transformation. If we look at the nucleus here, this is the parent. Notice this one here, this is a neutron, and after it turns into a proton, it stays in the same spot. So it's still inside the nucleus. It's just one of the neutrons flipped into a proton. What that means for our daughter nuclide is that the mass number stays exactly the same because a proton and neutron each have a mass of essentially 1. So the mass number stays constant, but the number of protons is now 1 higher because a neutron flipped into a proton. So my bottom number, the atomic number, goes up by 1 in the daughter nuclide. In the process, though, of course, we produce this electron and antineutrino, and those fly off, and that's what we sense as radiation elsewhere. So parent nuclide turns into a daughter nuclide with 1 higher number of protons, but the same mass number, and then also an electron and neutrino, antineutrino, fly off as radiation. Beta positive decay is just the opposite situation. So here we have a proton that turns into a neutron. In the process, since the proton was a positive charge, the neutron is neutral, so it has to produce another little positive carrier, charge carrier. And it's essentially the same thing as an electron, but it's an electron with a positive charge, which up until now is probably something that you didn't know existed. This has a special name. We call it a positron. Sometimes we also call it an anti-electron. But the positron is everything that an electron is. It just has a positive charge instead of a negative charge. In the process, we also create this neutrino, which is the opposite of an anti-neutrino. So beta positive decay is kind of the reverse of beta negative decay. And with that, you'll notice that since the proton flipped into a neutron, the mass number stays the same, but the number of protons goes down because we've lost a proton to become a neutron, and then we produce a positron and neutrino as well. All right, so looking at all of the beta decay together, we can use that to predict just like we did with the alpha decay. So here, this first one is already done for us. Thorium decays into protactinium, producing this -1 electron and the antineutrino. You'll notice here that the numbers still work. So 234 is equal to 234 plus 0. There's no mass to the electron. 90 is equal to 91 minus 1. So the math still works there. Here I have 131 and I end up with 131. So I know that my mass is going to be 0. And in this case, it's going to produce an electron. This is beta negative decay. I know that because the number of protons goes up by 1. So I'm producing this negative electron. I also know that because it has an antineutrino. This antineutrino always goes along with beta negative decay. And one way that you can remember this negative electron, that minus sign, often looks a lot like the bar on top of the antineutrino. They always go together. Here I've got carbon. Carbon 14 can decay into nitrogen 14. Well, to get nitrogen 14, the mass number doesn't change because in beta decay, the mass number doesn't change. Protons and neutrons just change their identity. And in this case, this is beta negative decay. One of these protons turns in, or one of the neutrons inside carbon turns into a proton. So 6 goes up to 7. And that is why the identity changed because 7 is no longer carbon. If you find 7 on the periodic table, that is nitrogen. Finally, here we've got magnesium decaying into sodium. Here, you'll notice that this is a positive electron, so a positron, that this is beta positive decay. To make the numbers work, 23 stays the same, but 12 goes down to 11, and that's what made it sodium. So you will need to be able to predict these and know the difference between beta positive and beta negative decay. There's one last type of decay that we'll be talking about, and that's gamma decay. This rarely happens just by itself. Oftentimes, we'll see gamma decay happening in conjunction with alpha or beta decay because it's already emitted this particle, this alpha particle or a beta particle like a proton, or sorry, a beta particle like an electron or a positron. And then it also has this extra energy. That excess energy we represent as a little asterisk there attached to that thorium nucleus, and it emits this energy in the form of just pure energy. So a gamma wave. This symbol here is the symbol gamma, and we are going to use that to define a not a proton, a photon of light being emitted out from that nucleus. All right, as I mentioned before, all of these, the math always adds up. If I look at just one row of numbers, 238 is equal to 234 plus 4, or 92 is equal to 90 plus 2, 234 is 234 plus 0, 90 is 91 minus 1, and so on and so forth. All of these, the numbers add up. So if you're looking for an easy way of finding the numbers, it's going to be simple math. Sometimes you might need to look up on the periodic table to identify what the numbers represent. But overall, the numbers, as long as you can recognize what type of decay is what, will always work out in the same way. So let's look at all these particles. You'll notice that I was using the same notation as I did looking at, for example, what we saw at the very beginning of the video, magnesium 2512. Here, a proton is represented with just a lowercase p. Proton has a mass of 1 and an atomic number of 1 because atomic number is equal to the number of protons. A neutron is a mass of 1, atomic number of 0. Electron is a mass of 1, an atomic number of minus 1. Whereas a positron is the opposite, is a plus 1. Um, so you'll see us describing these particles in this fashion. You'll also see down here the alpha particle. We'll either represent that with an He for the helium nucleus or an alpha um, Greek letter. Then these last two, this kind of italic V, here is an antineutrino with the bar on top or a neutrino down below. We'll see later on when we get into the different fundamental particles that there are more than one neutrino. These are specifically electron neutrinos. That's what that little E, subscript E, stands for. But there are two other types of neutrinos that we'll be introduced to later on in this unit as well. So a sample IB question here to get at your understanding of what's going on. Which of the following correctly identifies the three particles emitted in the decay of the nucleus of calcium 24 or calcium 45 rather into a nucleus of scandium 45? Well, here you'll notice that the mass number does not change. The example of the mass number not changing was one of the beta decays. Alpha decay, the mass number changed by 4 because the helium nucleus had a mass of 4 that it lost. So I know that beta decay is part of this and alpha decay is not. That very quickly narrows it down to the one correct answer, which is B. But you'll notice that it isn't just a beta particle that is produced. This beta negative particle is including also this antineutrino, as well as some gamma radiation kind of combined in with that. So like I mentioned before, gamma often is in conjunction with alpha decay or beta decay that's already going on. All right, so now that we have this radiation flies off, either in the form of an alpha particle, a beta particle, or some gamma waves. Something can happen because of this radiation. You've probably heard that radiation is dangerous. Well, why is it dangerous? One of the things that can make radiation dangerous is its ionizing ability. So if it smacks into atoms, say in your skin, for example, it can ionize the atoms inside your skin. What that means is that these particles can smack electrons and liberate them out of the atom and give them a charge. And by doing that, if you mess with enough different atoms, it can potentially mess with DNA and can potentially lead to cancer or other harmful effects later on. So, for ionizing radiation to happen, the more mass that you have, the more efficiently these particles can smack electrons off. So, an alpha particle then has the most mass. So it is then the most ionizing of those. Now, you might think that that means it is the most harmful. Well, there are other factors here that affect it. These different particles, these different radiations, have different penetration, which means that they can go through different materials. Alpha particles can be stopped by just 5 centimeters of air. Alpha particles don't travel very far because they're pretty big. They're big chunks of matter. You can also block alpha particles with just a simple piece of paper, or your skin is generally good enough to stop alpha decay or alpha radiation. Beta particles are just an electron or a positron, and that being significantly smaller than a clump of two protons and neutrons, can travel significantly farther. It can go through about 30 centimeters worth of air. It can easily travel through paper, but it can be stopped by something like a sheet of aluminum. So while it is more penetrating, it is not penetrating uh, infinitely through anything. Gamma radiation is highly penetrating. It can easily go through any amount of air. It can travel easily through paper, through aluminum, but it can be stopped if you have something very, very dense like lead, which is why you may remember like going to an X-ray. X-ray is a form very similar to gamma radiation. They're releasing that energy. And X-rays, if you've ever had one, you have to wear a lead vest usually to prevent this extra radiation from entering parts of your body that you do not want it to. So to focus it just where you're getting that X-ray image. All right. Another part that you should understand with these different particles is what happens to them and how can we manipulate where they go. So remembering back to the right-hand rule, uh, your thumb points in the direction of the current, your fingers point in the direction of the magnetic field, and your palm points in the direction of the force. So in this case, it's pushing out of the screen. I know that here because I'm using the notation of a dot being out at you and an X being away from you or into the page or into the screen. Now, if I use this right-hand rule to predict the direction of a force, I can think about what happens to these particles or this radiation as it travels through a magnetic field. And all particle accelerators use magnetic fields to help control or direct these particles and accelerate them up to really high speeds. So here, let's imagine that we have this magnetic field that is out of the screen. So it's currently coming out at you, which means that if I look at the particle, first, I need to think about what its charge is. Well, gamma radiation has a charge of 0, which means that there is no current that flows because of gamma radiation traveling. Gamma radiation is just going to travel straight through a magnetic field, that there is no deflection at all because there is no charge, and because there's no charge, there is no movement of charge or current causing that interaction between the magnetic field and the current. If I look at an alpha particle is two protons, which means it has a positive 2 charge. The neutrons don't affect it at all. Positive 2 charge is kind of like the direction of the current. So think about your right-hand rule. Put your thumb in the direction of the current, thumb going in this case to the right, and your fingers coming out of the screen. Your hand is oriented in a way that pushes downward. So an alpha particle in this particular scenario is going to be deflected downward as it's traveling through. And the reason, again, is because conventional current is defined as the direction of the positive flow. That means that a beta particle, specifically if we're looking at, in this case, beta negative decay, um, beta positive would be the opposite, but beta negative decay in this case is an electron that's traveling through. And you might remember for an electron, if we're going to use the right hand rule, the current is essentially opposite the flow of the electron. The fingers are still pointing out of the screen or out of the field. So we are going to experience that upward force. And you'll notice here that I've drawn in that deflection to be more significant than the deflection of the alpha particle. And this actually kind of gets at Newton's second law a little bit, F equals ma, that the less mass we have, the more acceleration, the more deflection, the more change in our direction we are going to see. So because a beta particle, this single electron, is significantly less massive, it has significantly more deflection, even though it's only half the charge. So it is experiencing half the force over much, much less mass, and will experience a larger deflection. Another way that we could deflect this radiation is by traveling it through an electric field. Remember that like charges repel and opposite charges attract. Here, gamma radiation, no charge, no deflection. But an alpha particle, this positive charge, is going to be attracted to a negative terminal or negative plate and repelled from a positive. So if I send it through this electric field, it's going to try to move toward the negative and away from the positive, and it causes it to deflect a little bit downward. It has enough speed that it doesn't hit the plate necessarily. It just bends it a little bit as it travels through. Same thing here with a beta particle. If it's a negatively charged beta particle, it is attracted to the positive, repelled from the negative, and since it is less massive, more deflection. All right, here is a summary cheat sheet of everything that you might need to know about alpha, beta, and gamma decay, from their relative charge to their relative mass, their penetration, what they are, how fast they typically exit the nucleus with what kind of velocity, how we notate what they look like in a nuclear reaction, how good they are at ionizing, and how you can stop them with some sort of extra material. All right, looking back at this idea of a valley of stability, here you'll see that this chart is a little bit more detailed than the one that we saw before. The one that we saw before had this line showing us what it would be if the protons equal the number of neutrons. But now, in addition to just the dots, we see these shaded areas. This green is the beta negative emitters. This orange area is alpha emitters. And this yellow area is beta positive emitters. And this graph is graphing on the y-axis the number of neutrons and the x-axis the number of protons. So let's look quickly what this radiation looks like in terms of these axes. Here, if I have alpha decay, that means that I am losing a proton two protons and two neutrons. So I go down two in protons and down two in neutrons. I'm essentially like skipping over two and two going down and to the left. This means that my mass number is decreasing by 4 overall. And I can see some example of what that looks like. Beta negative decay, I am keeping the same number, same overall mass number. That doesn't change. But my number of protons goes up and the number of neutrons goes down because the neutron turned into a proton. Beta positive decay would just be the opposite. The number of protons would go down and the number of neutrons would go up. So here, an example, alpha decay, we start with radium, and that essentially loses a proton number, so 2 proton numbers in the process. So radium turns into radon. So if we're looking at the periodic table in a line like this. If we started with protactinum, that's number 91, beta negative decay means that we are increasing our proton number. So protactinum becomes uranium. And if we put this all on a chart, we'll notice that this doesn't necessarily stop with one particular element going through one type of decay. This can happen over and over and over again as these elements change their identity through this form of radioactive decay. First, if you start with uranium 238, it can undergo alpha decay. And alpha decay decreases the number of protons and the number of neutrons. So now instead of 92, we have 90, and number 90 is thorium on the periodic table. You'll also notice that the mass number goes down by 4. So 238 goes down to 234. Thorium can undergo beta negative decay. When it does that, it increases its proton number by 1, which turns that into 91, which is protactinum. It actually undergoes that again to produce uranium. But now instead of uranium 238, after these 3 decays, it's now uranium 234. So it's returned to that. Now this process continues. So you can undergo alpha decay, beta decay, until ultimately it finds itself in a much more stable configuration. On this chart, we're basically zigzagging until we land in this valley of stability. And it is possible to predict, if you know the type of decay that's going to happen, to predict the atom, the nuclide that is formed after each step in the process. In the end, this decay of uranium ultimately ends with lead, but that is many billions of years into its future, because each of these steps takes a certain amount of time. And to be able to predict how much time that takes, we need to understand something called half-life. Half-life is the amount of time it takes for one half of the original sample to decay. That doesn't mean that the sample is gone. It doesn't like evaporate off into something else. It just is converted from uranium or some other type of radioactive isotope or nuclide into its next step in this process, just like we saw here. So every half-life is telling you how long it's going to take for that element to become half the next element. And we see this decay kind of goes down in this exponential format. This can be in the scale of seconds, minutes, days, or even billions of years. And you can see a huge uh, variety of half-lives shown just in this small table here. We'll see that again in a minute. So the first thing that you need to know about half-life is just what it does to the percentage overall. If I start with 100% after one half-life, 100% divided by 2 is 50. Then I have 50%. So after the next half-life, 50 becomes 25. 25 becomes 12 and a half, 12 and a half becomes 6.25, and 6.25 becomes 3.125. And it can keep going. At a certain point, the amount of that original sample becomes next to nothing. It doesn't become nothing. We keep getting closer and closer and closer as we level off to become very, very small in the amount that's remaining. And the length of this half-life, again, depends on what type of element we have. If we have something like radium-226, that is a half-life of 1,600 years. So instead of writing one half-life, two half-lives on this x-axis, I'm going to put an x-axis of time in years to show that after 1,600 years, I now have half of my sample remaining as that radium-226. I can keep going and just add that amount of years for each of these further half-lives. So if I wanted to figure out how much was left after 6,400 years, I can see that now. Well, that's about 6.25% of the original sample that's left. If I wanted to look at something else like astatine 217, now my x-axis needs different labels. Now we're going to look at a time in seconds, and we'll see it starts at 0.03, but it's very small. It just keeps adding up. So now I get to that 6.25 in just 12 tenths of a second, or 12 hundredths of a second. So 0.12 seconds to become that small, which means astatine doesn't stay radioactive for long because it emits all of its radioactivity very, very quickly. It makes it more dangerous if you are there when it is emitting all of that radioactive. It's very, very active, but it removes its radioactivity very, very quickly. So what you might see as a math problem using half-life is usually pretty simple. You're not going to need to do very complicated equations for this IBSL curriculum. So if I wanted to look at how many half-lives it takes for 100 grams of a radioactive sample to decay and become 12 and a half grams, I just think about it cutting in half. So 100 becomes 50, becomes 25, becomes 12 and a half. All right, I've arrived. How many times did I have to cut in half? Well, one, two, three half-lives happened to get it from that 100 grams down to 12 and a half grams. If that half-life takes 7 years for that particular radioactive sample, we can figure out how long that takes because it happened three times. Three half-lives times 7 years per is a total of 21 years total. Then if I take my half-life of radium, which is a different element in this case. And I know, for example, that that half-life is about 1,600 years. What percentage remains undecayed after 4,800 years, approximately? Well, I just need to figure out how many half-lives have happened in that amount of time. If the half-life, one, is 1,600, and total I have 4,800, 4,804 divided by, oh, that should say 1,601, should give me about four half-lives. Um, and we can see that progression along the way. So again, there's an error in this particular slide. We would find that number of half-lives in about the same way, but the numbers here don't quite add up. But we can figure out how many half-lives, which then can figure out how much is remaining. Let's look at one more example here. How old is a sample of rock that has 6.25% of its original carbon-14? The half-life of carbon-14 is 5730. This is a type of science that's used quite a bit to radioactive uh, or radiocarbon dating. It's a way of determining how long ago some organic material has decayed. So in this case, probably wouldn't be done with rock, maybe some organic material that was captured inside that rock to help us date when that rock formed around it. Here, if we know the half-life, we can look to see what our x-axis is going to be and how long it takes us to get to that 6.25 decay level. Well, carbon has a half-life of 5,730 years, so we can figure out what that is for each half-life along the way. And it looks like to get all the way down to 6.25, that is 4 half-lives later, which is 22,920 years. Another way that we could look at that is just saying, okay, 100 went all the way down to 6.25. To do that, we had to cut it in half 4 times. Well, 4 times that total half-life gives me that 22,920 years. All right, so from this video, we've done a lot. You should be able to talk about different types of decay, so radioactive decay like alpha, beta, and gamma decay, how it affects the nucleus of the atom that was decaying, and then use that understanding of decay to know what that radiation could do, its penetrating ability or ionizing ability, and how it can be deflected. And then with that, understand how the amount of decay that happens over time can be predicted using this understanding of half-life. We will only see examples in this class that use whole numbers of half-lives, but of course, you don't only have to land on one of these numbers in real life. Most times you are not going to land on a perfect number, but it gives us a good approximation of how long something needs to be for its material to radioactively decay.